Good morning. It's August 21st, and this is your daily brief in science. Here's everything you need to know. A new study asks if Earth microbes could survive on the Moon and finds that 3 bacteria and 2 fungi commonly used in space missions could endure lunar conditions by entering cryptobiosis in permanently shadowed regions near the poles. The research highlights implications for mission planning, spacecraft cleaning, and site selection to protect pristine areas and prevent forward contamination as Artemis and international partners target the lunar South Pole in the 2030s. Despite contamination risks, the Moon could still serve as a natural laboratory to study microbial survival in extreme environments and to refine contamination control strategies for future crewed missions. Among the microbes tested, Aspergillus niger showed the greatest UV resistance and could survive in sunlit areas, though survival was defined as remaining alive for at least 1 Earth day, not longer-term growth. The Nobile rim and connecting ridge emerged as the most promising regions for microbial endurance, with Aspergillus noted for its pigmented, thick-walled cells that help shield it from radiation. Survival was modeled as dormancy rather than growth, suggesting microbes could persist without reproducing and raising concerns about contaminating scientifically valuable polar sites. The presence of surviving microbes could complicate scientific investigations by blurring lines between terrestrial contamination and genuine extraterrestrial life indicators. A new chemogenetic biosensor called HaloRasAR lets scientists visualize endogenous RAS activity in living cells with high spatial and temporal precision. By using a circularly permuted halo tag and the far-red dye JF635, it marks a major advance in studying RAS signaling without overexpressed constructs. HaloRasAR reports RAS activity across multiple compartments, including the plasma membrane and intracellular membranes like the Golgi, offering more physiologically relevant measurements. All supporting data are available from the corresponding author, with source data linked to the Nature article, confirming this is a primary research report in the biosensor and RAS signaling space. In experiments, HaloRasAR compares RAS activity downstream of growth factor stimulation and PKC activation, showing different upstream signals produce distinct spatial activity patterns. The tool ties fluorescence changes to the geography and timing of signaling, allowing assessment of whether activation is sustained or transient, and whether it's localized to specific organelles. HaloRasAR enables monitoring across cellular compartments, expanding insights beyond the plasma membrane to intracellular sites and improving relevance to native signaling conditions. The study notes that compartmentalized RAS signaling can influence drug responses, and measuring endogenous RAS activity in situ can enhance understanding of cancer biology and RAS-targeted therapies. Framed as a live cell pharmacology tool, HaloRasAR has potential to map how pharmacological interventions affect RAS signaling in different cellular contexts. Context includes the development and characterization of an endogenous RAS activity biosensor applied to living cells, with implications for pharmacology studies targeting RAS pathways. Applied to live cell pharmacology, HaloRasAR revealed subcellular specific inhibition profiles when testing a RAS G12C inhibitor and a GEF inhibitor, suggesting compartmentalized drug efficacy. Mechanistically, HaloRasAR combines a genetically encoded targeting component with a synthetic fluorescent ligand in a chemogenetic design, offering advantages in labeling control, brightness, and timing over traditional fluorescent proteins. A comprehensive review across multiple sources examines how large language models are used in healthcare, focusing on safety, security, and governance as these tools move from research into real clinical settings. The Nature article from 2026 brings together leading European and international institutions to assess AI in medicine, highlighting the need for rigorous safety evaluation, transparency, and integrated oversight across research, clinical practice, and regulation. It also notes pervasive informal use of LLMs in clinical environments, often without formal institutional guidance and with rising data protection and accountability concerns. Regulators are pointed to gaps, as only a small share of AI systems are formally approved as medical devices and current regimes struggle to keep pace with adaptive AI, prompting calls for continuous evaluation and monitoring. The review uses a broad taxonomy to map risks across design, training, deployment, and clinical use, and it cites practical implementations like chat EHR and autonomous AI agents to show translation from research to care. Recurring themes include evaluating AI in clinical decision support, retrieval augmented generation in medicine, and ensuring robustness and reliability of healthcare AI systems. Safer use strategies proposed include secure development practices, careful data curation, systematic evaluation, continuous monitoring, clear institutional responsibilities, and both local oversight teams and centralized security operations centers for AI. Cybersecurity concerns address harms from digital health tools, phishing risks in health institutions, and the broader cyber attack implications for electronic health records. The discussion references venues such as Lancet, Nature, NEJM AI, NPJ Digital Medicine, and JAMA Network Open, underscoring the multidisciplinary scope of safety and governance. Risks are categorized into security threats like data poisoning and prompt injections, model inherent safety issues such as hallucinations and overfitting to expectations, and human-AI interaction risks including automation-driven biases and confirmation bias. A recent international study digs into tsetse bite mechanics and finds that feeding success comes from a combination of tiny teeth, backward mouthpart strokes, and adaptable behavior across diverse skin types, not a single specialized tool. Researchers describe tsetse as pool feeders rather than syringe-like attackers, and say their versatility in penetrating various skins explains their broad host range. The study uses high-tech imaging, biomechanics, and skin models to understand feeding mechanics across different hosts. Sleeping sickness has fallen to historically low levels thanks to surveillance, diagnosis, and treatment. But animal trypanosomiasis remains a major economic and health burden for rural communities that rely on cattle. Public health gains against human sleeping sickness contrast with ongoing animal trypanosomiasis, which continues to strain rural economies and livelihoods. Remarkably, the strongest forces occur during backward strokes, which act like a cutting motion rather than a simple puncture. Tsetse flies transmit sleeping sickness and animal trypanosomosis across sub-Saharan Africa, shaping transmission networks among wildlife, livestock, and humans. The virus-to-vector biology is a blend of anatomy, mechanics, and behavior that enables feeding across wildlife and domestic hosts, sustaining transmission cycles. Their ability to feed on many hosts strengthens transmission networks between wildlife, livestock, and people. Feeding mechanics show similar forces across different skin types, with backward movements causing more tissue disruption and larger blood pools for feeding. Understanding bite mechanics could inform future vector control strategies, even if no immediate method is produced. A link between the Epstein-Barr virus and multiple sclerosis is at the core of today's science story, with new vaccine and antiviral work aiming to reduce these conditions across populations. Ray Mainwaring's experience illustrates the stakes. She contracted mono at 13 and later developed MS symptoms, showing how EBV infection can precede MS and affect quality of life. EBV was discovered in the 1960s during work on Burkitt's lymphoma and was later linked to mono and other diseases, underscoring its long-standing significance. Vaccine development faces complexity, since EBV has roughly 100 genes. Moderna is pursuing both preventive and therapeutic vaccines targeting multiple EBV proteins. Beyond MS, EBV is associated with autoimmune conditions like lupus and Sjogren's syndrome and with certain cancers, pointing to broader opportunities for treatment and prevention. Current research includes targeted antivirals such as tenofovir alafenamide fumarate and ongoing EBV-focused vaccine efforts, with multiple trials planned to conclude by 2029. Two leading theories explain how EBV could trigger MS: molecular mimicry between EBV and brain proteins, and infected B cells acting as immune commanders that activate T cells against the central nervous system. A 2022 military cohort provides strong evidence, showing nearly all MS patients had EBV antibodies, suggesting that preventing EBV infection could prevent MS. Personal stakes drive advocacy, as Mainwaring, now 46, champions vaccines to protect herself and her children while managing ongoing MS fatigue, numbness, and relapses treated with steroids. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. We'll be back Monday with everything you need to know.